Questions about anything? Well, today I thought I would do something fun and show you some beautiful applications of the ideas we've been studying about uniform limits of continuous functions. So this is notation I was setting up in the previous lectures. I let CAB be the space of continuous functions on a closed interval AB. And one way of thinking of that as a space and the functions in the space as points is to define a distance between functions to be, that's called the uniform norm. It's the soup of the difference between f of x and g of x as x ranges from A to B, an absolute value of that. So that's how close those graphs are to each other on the whole interval. And of course, when the functions are continuous, that soup is a max, because the maximum would be attained for that continuous function. The book likes to write that as a norm, the norm of f minus g. That distance is determined by a thing that acts like a norm, like a vector distance between vectors. That's kind of a nice way to look at it, too. Anyway, we've been studying sequences of functions that are continuous on the closed interval. And the big facts I've been dealing with lately one, if Fn converges uniformly, so my symbol for uniform convergence, so let's see, Fn double arrow F means Fn converges to F uniformly. On the closed interval AB. So big facts is that if Fn converges to F, then the limit function has to also be continuous. That's a biggie. Another big fact is that if Fn is uniformly Cauchy, I don't know why I say Cauchy, it's Cauchy. Uniformly Cauchy. This is actually an if and only if. I did only one direction of it. The other direction is easier. Let's see. So Fn is uniformly Cauchy if and only if Fn converges uniformly. To something. And so now, because of 1, uniformly to an f, which is also continuous on the closed interval. God. That's an if and only if. And let's see, 3, if Fn converges to F uniformly, then the integrals are going to converge. Then the integral of Fn dx would converge to integral from A to B of f dx. That turns out to be a snap. I'll show you the demonstration in a second, as n goes to infinity. Okay, 3 is going to be a snap, easy. And then finally, I want you to know the Weierstrass M test. Let's say we have Fn in the continuous functions on an interval, And we have each fn of x is bounded by an mn on AB. Then the Weierstrass M test says that if that sum of the mn's is finite, if the sum of the mn's is finite, then the sum, as n goes from 1 to these partial sums of fn of x, converges uniformly to a continuous function. And of course, when it converges uniformly, we know that the limit function would also be continuous. Okay, so those are the big facts. And let's see, last time you might have noticed I was in a hay fever haze and kind of botched up my presentation a little bit. That's yesterday's stuff. I'm going to fix some stuff. Let's see, so I showed that uniformly Cauchy sequences converge uniformly. Okay, there's only, what did I do here? Okay, so when I was doing it, first of all, I noticed that pointwise, being uniformly Cauchy would mean at pointwise, fn of x is a Cauchy sequence. So we know fn of x converges to something. And that's how we define the f of x. So we get a pointwise convergence. The important thing was to get a uniform convergence. And so let's see. I said pick an x in AB. That was the correct thing to say. I want to show that f converges uniformly to that f. Then I let epsilon be bigger than 0, and then I used the definition of being uniformly Cauchy. And I took epsilon over 3 there because I'm going to play games and do a 3. Actually, I could have taken it to be epsilon over 2. I'll fix that today. And I should put an x there. That was a mistake. The uniform Cauchy business, x is something that I picked and fixed. It would make more sense for me to put here y's. So that would be when I get that less than epsilon over 2, when n and m are bigger than n, and that would be for all y in the interval AB. Okay, that would have been a better way to say it. Wish I'd done that. Now to see that I get uniform convergence, there's only one trick here, and that is to add and subtract things that make that it possible to estimate that using the definitions. So I'm going to add and subtract an fm. The n is going to be bigger than my capital N above, and an m could be much bigger. Okay, that's the key here. N and m have to both be bigger than n. And so I'm dealing with an n that's bigger than n, a little n that's bigger than a capital N. And I have the possibility of making the little m much bigger. And that's the key to this argument. So when I do a plus and minus that inside the absolute values and do the triangle inequality, I get 2 pieces. This one was true for all. This was true for all y. The second one there, that was less than epsilon over 2 for all y. And so certainly it would be true for x. And x is fixed, and I know that fm of x converges to f of x. And so this is my big moment where I can take a big m as big as I want, so that that thing is also less than epsilon over 2. Okay? And I've just shown you, therefore, that this thing is uniformly convergent. Well, the x was arbitrary, and I got this difference being less than epsilon. So the things add up to something less than epsilon. Check. And since epsilon was arbitrary, I'll change these to 2's now that I fixed it. So that gives me uniform convergence. I had similar issues when I did the next big fact. Any questions about that, by the way? I'll post this now that I've fixed it. So let's see. I want to show that the limit of uniform limit of continuous functions is also continuous. And that was slightly more involved. I had to add and subtract 2 things, actually 4 things. I guess I'm adding and subtracting 2 things, and that makes a plus and a minus of 4 things. So let's see, the trick is I want to be able to compare f of x to an fn of x, and f of c to an fn of c. So that makes it clear to me that I should add and subtract fn of x and fn of c. When I do that and stare at it, the trick is always to use the triangle inequality and get 3 pieces like that. The inner, let's see, the first one and the third one are, I can bound because of the uniform convergence property. So x and c's, no matter where they are, I can use the uniform convergence to bound those. And then the middle one is interesting. I want to make it small. And this is where I use x close to c to get that one small. Okay. And I realize here now that I have this n, if I fix the n in this, I just want an n that makes the first one and the last one less than epsilon over 3. I can take the smallest n that does that, so I can, or at least the smallest n I know. I let n be equal to the capital N and hold it fixed now. And I know that capital N is continuous. So that means there's a delta so that I can make that inner thing, this one, less than epsilon over 3 also. Okay, so I did that correctly last time. I might have rushed it a little bit at the end. Anyway, I'll repost those notes so you have the correct version. Questions about that? Okay. Let's see. So what's the missing little pieces here? I showed that uniformly Cauchy implies converges uniformly. The reverse is of number 2 there. So here's some remarks. Let's see. This way for number 2, I did last time. That's the interesting direction. This way, that uniform convergence implies uniformly Cauchy is easy. And that's why I skipped it. Let's see, so if it's uniformly, if Fn converges uniformly to F, then Fn of x minus Fm of x. Okay, I want to show that small. And you realize, aha, what I know is that both Fn and Fm are getting close to F. So this time the trick is to add and subtract f of x. So let's see, I'll subtract minus f of x plus f of x. And then I would have minus fm of x. And now I do the triangle inequality and get that two things that are small here. Okay, so if n and m are both bigger than whatever capital N, I can make those the epsilon over 2's. And the uniform convergence then would imply I have uniformly Cauchy. So there's nothing to that one. It's not the interesting one. Oh, let's see. Oh, yeah. Here's the proof of number 3. It's easy. The integral from a to b of fn of x dx minus the integral from a to b of the limit function, which is also continuous, of course, is the integral from a to b of the distance, of fn of x minus f of x dx. Okay, and now let me take absolute values here. That would be less than or equal to the integral from a to b of fn of x minus f of x dx. And we know an estimate now for integrals, the basic estimate, that's less than or equal to the max of fn of x minus f of x if x is in AB times the length of the interval. And so if fn converges to f uniformly, this goes to 0. So this goes to 0 as n goes to infinity if the fn is converging uniformly to f on AB. So that's a no-brainer. Okay, so last thing to show is the Weierstrass M test. Let's write Sn of x is a sum as n goes from 1 to capital N of fn of x. Then, if I were to want to see if that was a uniformly Cauchy sequence, I would say fn of x minus sm of x. Why don't I take n bigger than m? That would be equal to the absolute value of the sum as n goes from n plus 1 to capital M of fn of x. And of course, that would be less than or equal to the sum of the absolute values by the triangle inequality. And those are less than or equal to the mn's. So this thing is less than or equal to the sum from n plus 1 to m of the m sub n's. And so I bounded that difference by the tail end of a convergent series. And it's a fact that the tail ends of convergent series go to 0. Fact. Tail ends of convergent series, of absolutely convergent series, tend to 0. Let's see, how would I show that? Let's write sigma n to be the sum as n goes from 1 to capital N of these mn's. That converges to something. Let's call it limit. I guess I've shown this before. Okay, and L is the sum from n equal 1 to infinity. So L minus sigma n tends to 0, and that's equal to the sum from n plus 1 to infinity. Okay, so this tends to 0 as n goes to infinity. And so that sum is also tending to 0. And of course, the thing we're adding up is even smaller than that. So 0 is less than the sum as n goes from capital N plus 1 to m of the mn's is less than something that goes, or less than or equal to something that goes to 0. So that's the squeeze theorem. Questions about that or anything? Okay, that's all. By the way, this Weierstrass M test, a principal place where it gets used is to see that power series converge uniformly inside their radius of convergence. So an application of the M test from history. Power series have a radius of convergence. And we get uniform convergence inside inside the radius of convergence. Let's see, so what would that be? Let's see, I get uniform convergence on closed intervals contained in x naught minus the radius to x naught plus the radius, where r is equal to the radius of convergence. If the radius of convergence is 0, it's a dumb situation to think about. This is the radius of convergence. That's a nice thing to know about power series. Okay, so the last thing I want to do this semester as material for the course is section 8.4, which is a wonderful section on the exponential function. And it's pure fun. So that's what I want to focus on now. I'm going to do it better than the book does it, I hope. You notice. So we want to cook up the exponential function and really understand it. And so until we do that, let's define. Let's see. What is the exponential function? It turns out that the exponential function is the unique differentiable function e of x such that e prime of x is equal to itself, 1, e prime of x is itself, and 2, e of 0 equals 1. That determines the exponential function. And if you have a function that does that, you can easily show that it satisfies all the key properties of the exponential function. Okay, that's going to be our goal here, is to show that. And all the basic properties follow from 1 and 2 in no time. Okay, that's what I'm going to be talking about. Well, we know that if we had an exponential function, then we know that it would be given by its power series, which is particularly nice. But so let's define en of x to be 1 plus x squared over 2 factorial plus et cetera, plus x to the n over n factorial. Of course, that's the convention that 0 factorial is 1. That's the sum. Oh, I have to make that k from 0 to n, x to the k over k factorial. An easy thing to show is that these things converge uniformly on any interval. Let's take an interval. So here's a claim. Claim en of x rather. When I teach complex analysis, it's got to be a z instead of an x. En of x as a sequence of functions is uniformly Cauchy on the interval, how about minus r to capital R? That turns out to be an easy thing to see. Let's do a y here. Let's have en of x minus em of x let me just do the positive half. Let's take my m to be the big, let's see, I want, m is going to be the big one. stick with minus r to plus r. This is going to be equal to the absolute value from n equals n plus 1 to capital M of x to the little n over n factorial. Okay. Let's see, that's going to be less than or equal to sum as n goes from capital N plus 1 to capital M of x to the n over n factorial. Okay, let's write that. And so let's see, the biggest absolute value of x could be is capital R. So that's less than or equal to the sum as n goes from capital N plus 1 to capital M of r to the n over n factorial. And I'm thinking of the Weierstrass M test here. Let's write that out. Let's see. That would be r to the n plus 1 over n plus 1 factorial plus blah, blah, blah out to r to the m over m plus 1 factorial I can pull the r to the n plus 1 out front. And then think about what's left. The first one's a 1. The next one would be a over, not a, r over n plus 2. The next one would be r squared over n plus 2 times n plus 3. Plus, and the last one would be r to the m, let's see, r to the m minus n minus 1 over something. N plus 2 times out to m. Anyway, this one, n plus 2 is bigger than n. So this is less than r over n. And this one's a lot bigger than. This is less than r over n squared. Plus dot, dot, dot. The last one would be r over n to the m minus n minus 1. Okay, and that's a geometric series. And so that doesn't add up to the whole geometric series. This is a geometric series of positive terms. And of course it's less than 1 over 1 minus r over n. One plus, which is less than 2. What? Let's see, I want that to be less than 1, so I certainly want n bigger than r. So that's what I should have said back here. In order to make this work, we want r over n to be less than 1. So we want n to be bigger than r. Anyway, because of that n plus 1 factorial and in the denominator in the front, that goes to 0 rapidly. So we get, and we get that this thing en of x minus em of x is less than r to the n plus 1. R is fixed, so who cares if there's a big power there, over, I'll put this in n plus 1 factorial. That's the biggie thing, making it go to 0. And then I get something here that's just a number, r over n. Well, let's see, that's less than I want to make that less than something. I should make, now that I see what I want, I can get whatever I want. So I really want n to be bigger than 2r. And the reason I really want that is because then this would be less than 1 over 2. This would be less than 2. The book does it that way. And then I get times 2 here. And that n plus 1 factorial in the denominator makes it go to 0. So I get this is less than 2 when x is in the interval from minus r to r. And this goes to 0 as n goes to infinity. And so we see it's uniformly Cauchy. And now we know that En is uniformly Cauchy, implies En converges uniformly to something. Let's call it E. And we're just on some interval from minus r to r, to a continuous function, E of x, which I'm going to show you is the exponential function. Okay. And now that big fact about convergence of integrals, I'm going to claim, let's see, notice that the integral from 0 to x of e to the t dt, not e to the t, e to the nt, e sub nt dt, that would be the sum as n goes from 0 to n of the integral of t to the k over k factorial from 0 to x. Let's see, that is, what's the 0th one? That is going to be, when you do it, 1 over k, let's see, 1 over k plus 1 makes that a k plus 1 factorial. So if you do each one of those, you're going to get the sum as k goes from 0 to capital N. Let's see, k is going to go from 0 to little n of x to the k plus 1 over k plus 1 factorial. Okay, so that's equal to x plus x squared over 2 factorial plus blah, blah, blah. The last one is x to the n plus 1 over n plus 1 factorial. Kind of looks like my e to the n thing. But there's something missing, namely the 1 term. So aha, I should add 1 to both sides. Add a big fat 1 to both sides. And when I do that, I get this fun identity that's going to be the key to my success here. 1 plus the integral from 0 to x of en of t dt is equal to e sub n plus 1 t of x. Put that in a box. And now I can let n go to infinity and use the facts I've been demonstrating lately. Let n go to infinity. I get 1 plus the integral from 0 to x of e of t, the limit function. We know that when continuous functions converge uniformly, the integrals converge. And of course, this one also converges uniformly, so this is going to converge to also e of x. So let's see, I'm using in this, that was number 3. That uniform convergence implies integrals converge. I'm using number 3 on the left. Okay, that belongs in an even bigger box. So the exciting moment here, good news, fundamental theorem of calculus means that d by dx to the left, d by df of the left side exists and is equal to derivative of 1 is 0, and the derivative of the integral by the fundamental theorem of calculus is e of x. E of x is continuous, so I know I can do that. Okay. Well, the left side is e, so what we get? We get 1, e of x is differentiable. Because the right side is e of x and it's equal to the left side. And that's the one I just showed you is differentiable. E of x is differentiable. And its derivative is what we've dreamed it should be. It's itself. And of course, what's e of 0? 2. E of 0 is 1. That would be 1 plus 0 plus 0 squared over 2 factorial plus 0 to the etc. forever plus dot dot dot. That's 1. Check. Okay, so now I can start having fun. Once you know this, I'm going to deduce all the basic properties of the exponential in no time flat. And a key lemma that I like is that if f of x is differentiable, and d by dx f prime of x equals k times f of x, then this f of x has to be a constant times e to the k of x. where C is equal to f of 0. I've done a lot of technical things today, so I'm going to save this for next time. I'll show you what I'm going to use it for, though, just so you can get revved up about it. Proof will be next time. It'll be a snap. It'll be kind of a fun thing to do. Kind of a Math 266 kind of thing. But here's how I'm going to use it. Let's think about. Here's a consequence. Let f of x be equal to e of x plus y. Then we're going to use the chain rule and see that f prime of x would be e prime, and think of x of y as a constant. I'm holding it constant. And so that would be e prime of x plus y times d by dx of x plus y. And of course that's 1 plus 0. And so this is going to be e of xy, x plus y. This is going to be 1 plus 0. And so we see, aha, f prime of x is 1 times f of x. So my lemma that I'm going to prove next time says f of x equals c times e to the 1x. Where c equals f of 0. Okay, f of x was equal to e of x plus y. And f of 0 is e of 0 plus y. That's e of y. So that c is e of y. And of course, this is e of x. And so the exciting thing is that we get the famous, that e to the x plus y is e to the x times e to the y. Famous fact about the exponential function. And for example, we'll be able to see that that implies the exponential function never vanishes, and various other things that are everybody knows about the exponential function. Anyway, it's pure fun. And the proof of that lemma is going to be pure fun. Any last minute questions about anything? Okay, that's enough for today.
Can you go up to proving that e to the x equals e prime of x? Whenever we did like the geometric series, you added a +1 and then purple, keep going up.
This?
Some more. Some more.